Hello, Alexander, physics students, and this is the second problem in circular motion, and I'm going to tie into how these equations are the same as linear acceleration problems. So we have the kinematics. They are the kinematic problems. So I'm going to tie that together and do problem 2 with it, and I think it'll make a lot more sense when once you watch this video. As always, though, email me with questions and videos if you want a problem done that I haven't done already, or you need something explained anymore. So please communicate if you are needing some assistance. Okay, so we're going to do problem 2. Okay, we're going to get started, and here it is. Okay, a tire, and we are going to, it gives us a few things in here, revolutions and a time, and it wants the angular acceleration. So, but before I go into that, I'm going to click the equation sheet. This is actually I saved this in the 9.5 unit folder in case you've forgotten yours at home, so you can always access it. Here are the regular kinematic equations here. Right? You see them, you know them, you love them. Well, look down here. Oh, wait. They look very much the same, except you got these weird Greek letters there. You got an alpha, and you got this W. I can't even remember what that Greek letter is. And then you got this up here. See, look. Ooh. Looks pretty much the same. Why don't I copy this, go into this other, and we'll paste. You're like, what's he doing? Look, we'll get rid of these other ones. And boom. Ooh, look. They're exactly the same. Oh, awesome. You treat them the same. It's just one is for angular and motion, and the other is for linear. And the first video tied angular and linear together, so that was the bridge. Problem 1 has some information about converting between angular and linear. It depends on the size of the wheel, right? It's the size of the circle that you're going around. A small circle will give you a larger linear. One trip around a small circle is a lot less distance than one trip around a large circle. So you needed the circumference as the bridge between the two. Watch the first video if you need help with that. Okay, so let's go to paint, and let's paint a picture here, right? Happy little physics equations. So what are we given? Well, let's do our kinematic pieces here. Kinematics, we have acceleration, but the new acceleration variable is alpha. I don't care if you use this A, okay? We want to know that. We don't want that. We want an angular acceleration. There it is, angular acceleration. That's what we want. We want this alpha. The old kinematic velocity initial now uses W initial, and we start from rest. Initial velocity equals 0. Wonderful. And it's in degrees per second if you wish. 0 is anything, so we can make any unit here we wanted. Okay, V final, which is W final. And we do not know that. It just says final angular speed. We do not know that. So put a question there. But this is the one they want. That's the answer. Okay. Delta x is our old one, our displacement. For this one, it's theta, or delta theta, or the angle that you go through, or we can just call it theta. But anyways, if you like delta x, that's fine. And we're told 4.60 revolutions. And then time is still time, and we have this. Now, as long as we have 3 out of the 5, it still holds. We can solve. We have, let's check, 1, 2, 3. Perfect. And so that leads us to the equation. We have delta x equals v initial t plus 1/2 at squared. Or if you prefer, the new delta theta is equal to W initial times time plus 1/2 alpha times t squared. Either way is good. Now, we do have to do one thing here. We need this in degrees, so we need to convert that. 4.6 revolutions. Okay. And in 1 revolution on the bottom is how many degrees? 360, right? Like me on a skateboard. That would be funny if I tried to do a 360 on a skateboard. In fact, me just getting on a skateboard and trying to go would be hilarious. And so when we convert this, 4.6 times 360, sorry I didn't have that one done ahead of time, is 1656 degrees. So, you know, we made, and we went around 4 times, and then another 0.6, which is that many degrees. So now we're ready to plug in here. We'll section this off, and we'll plug in and solve. Let's do something purple. So delta theta is 1656 degrees. I'll leave the units on this one. This is 0. Initial velocity is 0, so we can just call that 0t is still 0. So you don't need to put the t in there because 0 times anything is 0. So then we have 1/2 alpha, which we're solving for, and our time is 1.38, and it's squared. Please don't forget the squared because it's in the formula there. And then we solve. Oh, by the way, this is seconds. So what are we dividing? We're dividing this by 0.5 and then by this here, which is 1.38 seconds squared. So it's seconds squared. So when we do this, I ended up with 1,739.13. And what are our units? DEGs, degrees, and we divide it by seconds squared. Well, that makes sense because it's an acceleration. It's an angular acceleration. So you have a rotation unit divided by time squared. So that makes sense that it's a angular acceleration. So it has units of a change in angle over time squared. Okay, so 1739 degrees per second squared. So that's all it is, and so it's really nice how it ties into our previous units, our previous problems. So give that one a try. Give it a thumbs up if you like it. I don't know. I don't get too many thumbs up. Thanks, and I'll see you on the next problem.